R0 to R31. These are the some general purpose registers. Okay, general purpose registers. Percentage R0 to percentage R31. These are the ARC user visible registers. User visible registers. Okay, we use these registers percentage R0, R1, R2, R3, R4 till R31. So these are the 32 registers. Along with that, there are two other separate registers, that is program status register and program status register and program counter. These are also 32-bit registers. So you know what is the operation of program counter. Program counter that holds the address of the next instruction that is executing. Okay. Program counter 32-bit register that hold the address of the next instruction that is being executing. So program status register that gives the status of the like after performing arithmetic operation, if there is any carry flow flag or overflow. Okay, so that gives the status, that is PSR. Then now let us study ERC assembly language format. Okay, it is a assembly language. 8086 processor that you have studied, that is also the assembly language. Okay, ARC language format is the same as the Spark. Okay, it is also called as a Spark processor. SPARC. I think it is a scalable processor. ERC means a RISC processor, a RISC computer architecture, a RISC processor. The name they are given the processor as Spark. So this is the instruction format. Okay, label. Okay, label like in your 8086, like you used to give the some labels like up, down, like up, and some instructions, right? I think MOV in 8086. Okay, up or down. We used to give some labels. So it's similar to that here. They are given the labels. Then mnemonic. Mnemonic means the instruction. Add instruction. Then source operand. Source operand. These are the to perform the addition. We need two registers. One is from R1 and R2. These are just we are used these registers. R1 register and R2 register. Okay, these are the source operands and destination operand. Okay, and comment. We will specify the comment here, like content of register plus register. Which are the register we are used here? R1 and R2. Okay, then this is the one type of instruction. Then one more type of instruction is like lab2. These are label to add mnemonic. The add to perform the addition. One is here we used a register R1 and there is a constant value. So content of register, like suppose in the content of register there is a value like 10, and what is the constant? 12, right? So 22, where it stores in R3. 22, it stores in the R3 register. So register plus constant value. So that is 22 value, right? So this is the simple the representation of instructions. So we discussed add instruction where we are adding the content from the two registers R1 and R2 and storing in the R3, and then one more case storing from the content of one register and one constant value, right? Okay, then these are some more instructions that are related to like label 3, third type of instruction, that is load. LD means load operation, loading the data. So to perform the load also we use source and destination operand. So here we are loading the the content from this source operand to the destination operand. What is the destination? R3, right? R3 register. So loading R3, loading the R3 register from the content of the memory location that is specified in the register R1. This bracket indicates what? So this bracket is there here. So this bracket indicates the memory location that is available in which register? R1 register. So R1 is how many bit register? A 32-bit register, right? R1 is a 32-bit register. Like suppose this is on 32 bit means 8 hexadecimal value should be there. Okay. So 8 into 4, 32. So this location, okay, loading the data, loading the data from, okay, the data means this address, memory location that, so this is R1 register that contains a this particular memory location, right? R1 contains a memory. So this contains some data, okay? This contains some data. This address contains some data, okay? So here loading the R3 register, loading the R3 register from the content of memory location that is specified by the R1 register. Content of memory location that is specified by the which register? R1 register as per this. Okay. Here, like for example, to perform the addition, like one data is available here directly, they are provided in the registers and there is a constant value. Okay, but here what happens? Indirectly, the data is specified. So loading the R3 register from the content of memory location that is specified by the R1 register. Then for another load instruction, so this is the destination operand, right? So here the content of memory location that is specified by the R1 plus R2. Okay, R1 has some address, R2 has some address, and that address contains the data. So addition of that data will store in the R3. Okay, so loading, we are just loading the data, like store, like copy. Okay, loading the data in the R3. Then there is one more type load instruction. One is that content of memory, only one register is there, and here content of memory location that is specified by the R1 register, R2 register that you are performing addition and loading into this R3 destination operand. So in third case, what happened? There is a register and the constant value. Okay, constant value. So here the content of memory location that is specified by the R1 register minus this constant value, okay, and that we are loading into R3 register. R3 register. So this is the load instruction. Store instruction is opposite. Okay, it is opposite. So previously we used to load content of memory location that is specified by the register to the destination operand. Here we are storing the content from R3 register to the memory location that is specified by the R1 register. We are storing the data. We are taking some data, okay, from which register? R3 register, and that we are storing into the memory location that is specified by the R1 register. R1 has some memory location or some address. So in that we are storing. So it is opposite to the load operation. Similar to that again, R3, and this is the destination from R1 and R2. Okay, so load and store, it is complete opposite. Loading the data and storing the data. Then yeah, this is the same instructions. It is enlarged. Okay, same whatever we discussed, load instruction and store instructions. Then this is a simple example. Add two numbers. The figure shows a simple program fragment using the load and store instructions and add instructions. So here to perform z is equal to x plus y. Okay, z is equal to x plus y. So here load operation. Load operation means what? What is your source? This is the source. Loading the content of memory location. Okay, here some value is there here. X means some constant value they are taken. So we are loading this data to R1 register. Then another value that we are storing into the R2 register. Loading. We are loading the here it is just it is not a X means what? It is just some like representation like X means some data. Like consider 10. Y means 20. So that we are loading here. X1 make X1 what it contains. This is the comment how we specify. R1 register contains now 10 value. This is the how we specify comment. 20 in R2. Okay, now perform the add R1 R2. These are the source operand and this is the destination operand. This is the destination operand. Okay, R3 that contains the result. Then storing the R3, storing the content of R3 to content of R3. In R3 content the result, right? That you are storing into the memory location that is specified by the destination register. Okay. So yeah, this is a very simple example. Very simple example to perform the addition of the two numbers. Okay. Since the ARC is a load store machine, the code must fetch the x and y operands from the memory using load instruction, then perform the addition, and then store the result back to Z using store instructions. So this is not it is not that much difficult to okay. It is ARC is a very simple assembly language. Then okay, what we discussed here, the load instructions, store instructions, and addition instructions we have discussed. So the formats of load instruction. So this is addition instruction, right? Addition R1, R2, R3. So these are the addition instruction format, and this is load and store instruction format of ARC processor. Then next we'll discuss some more instructions, that is transfer of control sequence. Okay, so branch instruction. These are the branch instructions of ARC processor. What is the mnemonic? Branch always. Okay, branch always and label means if the condition is true, if the branch always, if the condition is true, then it will directly jump to the this particular address, the label, it whatever the label. Okay, like in 8086 we used to do jump down or jump up. Okay, so similar to that, branch always BA. Okay, so it specifies, it will jump, the program control will specify where to jump, where to go. The program counter that will specify the address of the next instruction to be executed. So it will specify where to jump. Then branch on 0. If the result is 0, the condition is satisfied, the branch 0, then it will jump to the particular label. The branch on non-zero, branch on non-zero. Okay, if the condition is true, then it will jump to the particular label, particular address. Label means it will be a particular address, like we are specifying here. This is the format. Huh? For every instruction, we have to provide the label first. Label, the instruction mnemonic, source operand, destination operand. This comment is up to you. It is comment is for to understand the operation, right? But this is fixed. Label we have to write label colon mnemonic, source operand, and destination operand. Okay. So a portion of the ARC, a RISC processor, ARC ISA is a subset of the Spark processor. So these are the some different instructions. Okay, the same have enlarged here. What are the memory related instructions? Memory related instructions are the load and store. These are very few important instructions only here, and we are discussing. Okay, in your syllabus, we are not studying in depth of our ARC assembly language instructions. Okay, only few important instructions of the ARC processor. So memory related instruction, load a register from the memory location. LD means load a register from the memory location. Then store means store a register from the memory. Store a register, the register content into the memory. Okay, load the register content into the memory. So this we discussed. Then there is one more instruction that is called the set high. We spell it as set high. Set, as you know, high means what? Logic 1. So load the 22 most significant bits of a register. Okay. Load the, what is this? The mnemonic or meaning? Load the 22 most significant bits of a register. Set high. Set high is the mnemonic that indicates is to load 22 MSB bits, 22 most significant bits of a register. Like if it is a 32-bit register, if it is a 32-bit register, then the most significant 22 bits, most significant 22 bits set high. We'll discuss okay the with examples, but this is the meaning of set high mnemonic. Then and CC and CC means bitwise logical and operation. Or means or CC, bitwise logical or NCC, so bitwise logical nor operation. Or okay, bitwise logical nor operation. Then SRL, shift right, add CC, call subroutine, jump and link, return from the subroutine call, jump and link, return from the subroutine call, branch equal, branch if equal. So these are some other branch instructions we discussed, in the last branch always, branch on zero, branch on not zero. Okay. So here the branch if equal, if the result is equal, if the condition is true, branch if equal, branch if negative, branch on carry, branch on overflow. If the result is overflow, if the result is carry generated, if it is a negative, branch always. Okay. So these are the control. So whatever the call, jump, jump and link written from a subroutine call. Subroutine means it is a small code. Okay. After executing the code, it will return. So these call, jump, L, branch equal, branch negative, E branch if negative, branch on carry, branch on overflow. branch always. So these are all which type of statement? Control statement. Okay, and add cc means arithmetic instructions. Add cc is a arithmetic instructions. Then these set high. Then set high means we are setting the high logic 1 to most significant 22 bits, most significant 22 bits, and or nor, then shift right. Okay, here they are mentioned only the important instructions, that is mnemonics, and this is load and store, memory related instructions. Okay, so this is very important for your exam point of view, the ARC assembly language instructions. Okay, ARC assembly language instructions. So which are the types? Memory related instruction, logical type of instructions, okay, arithmetic instructions, then control, okay, control instructions, then load. So this is just the description of those instructions. Yes, load is load a word into a register. Load a ld means load a word into the register. Store means store a word into memory. Store a word into the memory. LDUB. LDUB means load unsigned byte. These are some mnemonics. Okay, these are the some mnemonic. These are the some of the mnemonics. Load unsigned byte. That is fetch a byte and pad with zeros. Load unsigned byte. Load signed byte LDSB. Load signed byte. Okay, fetch the byte. Fetching means you are fetching the byte, and sign is extended. Load signed byte. Load unsigned half word. Load unsigned half word. Load signed half word. Load signed half word. LDSH. Load unsigned. UH means unsigned half word. Half word means 16 bit. Half word means how much? 16 bit or 2 bytes. Okay. Load signed half word. Store byte. Store, yes. Okay, ST. Store byte, store half word. These are the few mnemonics. Then add CC also we use. Add CC. These are the mnemonics. Add A plus B operation, sub A minus B, and logical A and B operation, and N. And N means it performs the like A and the inversion of B. Okay, bitwise, and the second operand is complemented. Okay, here operation is logical and, but and n means the second operand is complemented, then or A or B. Okay, these are the mnemonics. Or n means again the or operation, but second operand is complemented. XOR operation, XNOR operation. These are the important uh, the mnemonics of ARC processor. Okay, so these slides you will get from here. You can see at the bottom Mudoka miles. Mudoka M means miles. Mudoka miles. This is the textbook Computer Architecture and Organization by M. Mudoka. This PPT you will get from the internet. Okay, I will, even I can share in the Google Class also. So is there any doubt? So what we discussed today? just mention in the chat what we discussed in the what are the different type of instructions. Mention it, all of you. All of you mention the different instructions, the mnemonics, what type of mnemonics we discussed in the today class. Mention it. I want to. Yep. Otherwise, you can just unmute it and yes, say unmute it and you can tell some of the instructions, or you just mention in the chat.
Yes, sir.
What are the instructions?
Sir, add instruction, we have seen how it works.
Hmm.
That we've seen some operations such as and or in the instructions which we have in the in terms of the logic gates.
Then so we discussed what are the different registers. The registers we represent using the percentage, R0, R1, R2, R3, like percentage R31. So like the 32 registers are there to store the data. So these are all 32-bit user visible registers. Okay. And the register R0 has by default value 0, and the registers R4 and R5, the registers R14, and R15s are used as a dual operation. R14, it is also used as a stack pointer, and R15 as a link register. Then program status register, there are two separate registers, so total 34 registers, total 32 plus 2, program counter and program status registers. And these are the some mnemonics. Add. Okay, what is the operation here? Label colon add R1, R2 and R3. Add percentage R1 comma percentage R2 comma percentage R3. So these are the instructions how we represent. Then load instruction, store instruction, and in the comment you can understand what is the operation of those instructions. Okay, so these are the load and store instructions. With one example, to perform the x plus y, we have to first load the content, these are x and y value into the R1 and R2 register, then perform the addition, and after here we'll get the result in the destination of R1. From this to that z value store, we are storing into z register, we are storing into the destination register. That is okay. Then branch instructions. Branch always means if the condition is true, these are all branch instructions that will jump to the particular address or label. Okay, so these are the some important different type of mnemonics, memory related instructions. What are the memory? Load, store, set high and cc. Load and store are memory related, and logical related is set high and cc or ncc. Logical operations, write, shift right, logic, then arithmetic operations and call, jump, okay, branch equal. These are all control branch always, branch on carry. So these are all branch related or control related instructions. There are a few more the mnemonics, that is load. These are some descriptions of a LDUB, load unsigned byte, load signed byte, okay, load unsigned half word, LDUH, LDSH, STB, store byte, store half word. Okay, so these are all some arithmetic and logical mnemonics. Okay, so this is about the different ARC instructions. And so is my screen visible? Yes. Say anyone else?
Yes, sir.
Okay, so ARC instructions and
PSR format. This is very important for your exam point of view, and you will get a question. Write the different ARC instructions. ARC instructions. So in the last class, we discussed about different registers. There are 32 registers plus 2 registers, PSR and stack pointer. Okay. So ARC instruction, a RISC processor instructions, as we discussed in the last class, like load instruction, LD, store, load unsigned byte, load, okay, load the signed byte, load unsigned half word, store. Okay, these are the instructions we discussed, and these memory related instruction, LD, ST, set high, load the 22 most significant bits of the register, then AND CC, bitwise logical AND, or CC, bitwise logical or NCC, bitwise logical NOR, or NCC, shift right logical. Okay, and then arithmetic and add CC, add operation, then control instructions, call, jump L, branch equal, branch if equal means jump, it will jump to the particular, the condition is true, branch if negative, branch on carry, branch on overflow, and branch always. So these are the different control instructions, right? So now let us discuss very important concept that is in your exam point of also it is very important, ARC instructions and PSR formats. Okay, a RISC computer instructions, right? So the, means each instructions is having a format. Like for example, in 8086 also the instructions are having their own format, how they represent the data. So I think it is visible. The same screenshot, whatever the image is there, no, that I have enlarged here. Is it visible? Yes, say anyone yes. Actually, I can't see the message. So what you do, you just orally you can say yes or no.
Yes, yes, it's visible, sir.
Okay. So these are the formats: set high format, branch format, call format, arithmetic instructions format, memory format, and for your examination point of view, this is very important. Okay, so just pay the attention. First is set high. As the name indicates, it's a set high format. Set high format. So in the set high format, so set as indicates the logic 1, set high format. Okay, so what it does, here you can see it starts from the 0, means total 32 bit it is. Okay, 32 bit the size of the instruction. So these 22 bits, okay, from 00 to, you can see 00 to 21, yeah, okay, up to this level 21 bit means 00 to 21 means total 22 bits. Okay, so that is called as the immediate 22 bit, means it will place the 22 bit here from 00 to 21. So set high means it will place the logic 1 set high in 22 bits. Okay, then after that, here if the 30th bit and 31st bit, if these two bits, if it is 00, if it is 00, okay, 30 and 31 bit, if it is 0 and 0, then it is called as set high or branch related instruction. Which type of instruction? Set high, or so as I can tell you what is set high, as we discussed, it's a memory, it's a logical related instruction. It loads the 22 most significant bits of a register. Okay, what it does, 22 most significant bit. Like for example, suppose some data is there, 32 bit. Okay. So how many? Some data, 32 bit register. So it will consider the most significant how many bits? 22 bits. 22 bits most significant registers. Right? How many? 22 bits most significant bits of a register. It loads the 22 most significant bits of a register. Okay, so here set high. So in the set high format, it loads the 22 bits of a register. 22 bit of a register. Then so the one concept you are understood, that is if the bit is 0 0, 30th and 31 bit position, if the 30th and 31 bit position is 0 0, okay, then it is a set high or branch format instructions, right? Set high or branch format instructions if 30th and 31st position bits are 0 0. Okay, then here it is OP. Here you can see the format. If the operation means opcode operation, here different operations are there. So here OP, if it is 0 0, then it is a set high or branch related instruction. If it is 0 1, then it is a call instruction. If 1 0 means that 2 bits 30 and 31 bit position. If it is 1 0, arithmetic type of instruction. If it is 1 1, memory type of instruction. Because we understand what is the instructions, English like statements, we can understand, human being can understand, but the computer, how it understands the instructions. So it is with respect to these data. Okay, suppose if the 30th and 31 bit position, if both are 0, then it understand that yes, it is a branch or set high related instruction. Suppose if it is 0 1, if it is a 0 1 call instruction, if it is a 0 1 call instruction, and if it is 1 0, then it is arithmetic type of instruction, and if it is 1 1, which type of instruction? Memory related instruction. Means computer will understand. So what is the instruction? Okay, suppose memory related means actually it convert that assembly into the binary form. Assembler, okay, assembler, it convert the assembly language into the binary form, and in the binary, so it will understand if suppose 30th and 31 bit position is 1 1, then it understands that okay, it is a memory related instruction, right? Then so set high format. So here set high format, it load the immediate means it load the 22 bit register, MSB bit 22 bit register here from 0 to 21, means total 22 bits. Then here OP2 for set high, so there is a OP2 operation. OP2 or OP2, OP1, these are all the operations. These are all the different operations. Okay, so OP2 means what? Here this is the OP format. OP means if these two 30th and 31 bit position. Okay, then OP2, here OP2, it is a 3 bit reserved for OP2 operation. Suppose if it is a branch instruction, if it is a branch type of instruction, then what is the value? 0 1 0. So here it will come 3 bits, 0 1 0. because here set high and branch is same. 0 0 indicates set high or branch. Okay, so once if it is branch or set high format, then how it differentiates? Okay, it is differentiate with respect to this OP2 operation code. Suppose if OP2 is 0 1 0, then it is a branch type of instruction, and suppose if it is 1 0 0, then it is called as set high instruction, set high format, right? So it is like, for example, now Prathamesh, like there are two members in your class, Prathamesh Kulkarni and Prathamesh Pawar, suppose. So Prathamesh, like these 30 and 31 bit indicate the same, no? Prathamesh. Set high format is Prathamesh, branch format is Prathamesh. I mean, both are, it indicates one person. Then to differentiate exactly, is he a Prathamesh Pawar or Prathamesh Kulkarni? So we need one more surname, right? We need one more surname. So with OP2 operation, we can identify, like if OP2 means if it is a 100, then it is a type of set high instruction, and if it is 010, it is a branch related instruction. Okay, then here the condition you can see. First we will go for, so first is that this one 30th and 31 bit position, and 22, 23, 24, these 5 bits are very important to differentiate whether it is set high format or branch format. Then after that, here the set high format, so this is the format. It loads the 22 bit and RD, the destination register. Okay, so the destination register, like it is a 5-bit register, whatever, like the register, different registers, as we discussed in the last class. What are the different registers? Total 31 registers are there, 32 registers. Okay, and we represent in this format. Suppose 3, suppose percentage R3, right? Percentage R3. So how we represent this? R3 means what? 3, binary 3, and we represent in this binary form. Suppose percentage R10. R10 means, what is the binary for 10? 10 10, and you add 0 here. So right. So now what is this? R10. So binary. Okay. So in this way, you have to write here. You have to write the destination register here. 1, 2, 3, 4, 5. There are 5 bits are reserved for the destination register RD. So I hope it is clear. Set a high format. So 30th and 31 bit are used to represent these 2 bits. 00, it is set high or branch format. And once it is confirmed, either it is set high or branch, then we go for the OP2. So OP2 means here, if it is 00 or 100, it will differentiate. 100 means set high, and branch means 010. These 3 bit will differentiate that. Okay. Then for set high format, immediate it loads the 22 most significant bit, 22 most significant bits, MSB, right? It loads the 22 most significant bytes here. It is reserved, 22 bits are reserved, and 5 bits are destination register. So total 32 bits. Then comes to branch format. In the branch format, so first 2 bit 00, there is branch. Then also 29th bit is also 0 here. 29th bit also 0. So it is fixed. 3 bits. 29, 30, 31. These are reserved to 0. Then condition. Means it is which type of branch instruction. Here you can see the conditional table. Suppose if it is a branch if equal, branch if carry flow, branch if negative, branch if overflow, branch if branch always. So if these are the branch instructions and there is a particular unique code for that. So branch equal, if branch is equal means 0 0 0 1, then branch on carry flow 0 1 0 1, branch if negative 0 1 1 0, branch overflow 0 1 1 1, branch always. So you have to place these condition here. 4 bit is reserved for condition. 4 bits are reserved for the condition. Then these 22 bits 0 0 to 21, the 21 bits that is reserved for the displacement. Displacement means to calculate the address, because branch means if the condition is true it will jump to some particular location. Okay, so to calculate that address we use this displacement 22 bit. 22 bit is reserved for that. Then third instruction is, format is call instruction format. So in call instruction, if the 30th and 31 bit position, if it is a 0 1, then it is a call instruction. And then the remaining 30 bits it is reserved for the displacement to calculate the address. Means call is also similar to the branch instruction. So call address means with respect to that whatever the address we mention, it will jump to that location. So for that 30 bits are reserved. Okay, so now I want to know from your side, are you getting these 3 instructions? Here you have to remember these tables also. You have to remember the tables also you have to remember. These OP, OP2, OP3, it is related to your arithmetic and memory instructions will come. Yes, just I want to know, are you getting this or shall I repeat once again? Am I audible? Yes. Sanskar Raut 46. Am I audible? Shall I repeat once again? Yes, 19, roll number 19. Shall I repeat?
No, sir. It's understood, sir.
Okay, 62. Emul,
Yes, sir.
shall
Yes,
I
sir.
repeat?
No, sir. We understood.
Then Meet, roll number 11.
Yes, sir.
Shall I repeat?
No, sir. Understood.
Okay. Then arithmetic is very simple. As you know, to perform the arithmetic, you require the 2 numbers and store store the result in destination. So these 2 bits, 30 and 31, it specifies, yes, it is a arithmetic type of instructions. Arithmetic means addition, subtraction, arithmetic operations. So here, this 30 and 31, then OP3. OP3, how many bits are reserved? 1, 2, 3, 4, 5, 6. So 6 bits are reserved for this arithmetic operation. What is that? Add CC. Add CC means 0140 and CC. And means logical and. Okay. For logical and 010001, then or CC 010010. You have to remember this table because we are not studying in detail. So in this particular, they are mentioned some important instructions. Then SRL, shift right, logical, shift right, left, shift right, logical. Okay, then jump L. Jump L. Jump L means it will jump. So here in OP3, you can see there are 6 bits are reserved, 6 bits, and here 2 bits are reserved for the 10 means it is arithmetic type of instruction, and to perform the addition we need 2 registers, right? So the content, the one number, suppose one number we will get, like for example, register 1, suppose 3, then register 2, suppose 5. Okay, means we are performing addition of 2 numbers, 3 and 5, and storing the result in destination register. So what is the result? 8, right? So RS1, how many? 1, 2, 3, 4, 5. Okay, so 5 bit means wherever we are using the registers, no, for that registers we are reserving the 5 bits. 5 bits we are 5 bits we are referring for the to storing the data in a register. So here source 1 means this 3 will come here. 3 means in terms of binary 0 0 0 1 0. Okay, so here I will show that. There is. Okay, I will write clearly. Okay, so this is 3, right? One data, then the second data for addition is 5. So 0 0 1 0 1, right? So it will take the data from this particular, means actually we mention the registers like some instructions. Suppose if it is percentage R3, okay, it is actually percentage R3. Some registers we are using. Suppose here 3 and 5, and 3 and 5 means 8, right? Addition, like here it will come 8. Destination register. So these 2 bits. So arithmetic means source 1, source 2, and destination register. And these bits, and one more important is 13 bit. If 13 bit is 0, it indicates that in the addition operation we are using the data from 2 registers. Data from the 2 registers. Okay. Suppose if this 30th bit is 1, if it is 1, then we are using the one data from register 1, and another is a constant value. CMM13 means what? It is a constant value. Okay, as we discussed in the arithmetic operation in the instructions, I think we discussed about that. Yes, here is okay. Eraser is not showing. So okay, so here this addition instruction, no, this is here R1 R2, store the result in R3. This is one type of instruction. Another is that R1 and some constant value, R1 and constant. So here we use SIMM13. SIMM13 means it uses the 13, the constant 13 bit is reserved. 13 bit is reserved. So these are 2 type of add instructions. SIMM13 means 13, 0 to 12. 13 bit is reserved for the what purpose? To store the constant value. Okay. So in arithmetic operation, what 2 type of instructions, right? two type of instructions. One is that content from both the registers and add the result in a destination register, and another is we are adding the content from registers and constant value and storing in the destination register. So this is about the arithmetic instruction. Then comes the memory related instruction. So in memory related instruction, memory format, so here the 2 bits, 30th and 31 bits positions are 1 1. So if these 2 bits are 1 1, that indicates it's a memory related instruction. It is a memory related instructions. And you know what are the memory related instructions? Load, store, okay, the memory related instructions here OP3, in case if the OP is 1 1. So what is the OP? OP is 1 1. If OP is 1 1, then it is which type of instruction? It is a memory related instruction. It is a memory related instruction. And in this memory related instruction, the OP3, so how many? 6 bits, 19 to 24, 19 to 24, 6 bits are reserved for this load operation and store operation. Load means all the bits are 0, and store means 000 100, and the rest is as usual same. For load operation, in the load instruction, suppose if we are using both the registers at the source operand, if both the registers we are using, then this is 13th bit, it is 0, 13th bit is 0, and if it is one register and one constant memory address, okay, then it is 1 1, okay, and again same as it is the destination 5 bit. So wherever we are using these registers, okay, RS1, RS2, RD, these are all, it reserved for the 5 bits. It reserves for the 5 bits. Here you can see the load instruction. Okay, here even we are discussed about this addition also, load and store operation. So load instruction, what it does, it stores, it load the content of a memory location that is specified in the R1 register to register R3. It loads into R3 register. Then store is opposite. It stores the content from R3 register to the memory location that is specified by the R1 register. Okay, from R3 to R1. Load and store operation. Here registers are involved. Here, so this 13 bit, if it is 0, 13 bit, if it is 0 means this will come both register and destination register. If 13th bit is 1 register and another is constant value. Okay, this one. Okay, CMM 13. So this is all about the instruction format. Then last one more is PSR, program status register. So this is 32-bit register, and here the 20th bit will specify the status of carry, 21 carry overflow, then 22 0, then 23, I think it is a negative N. So these are the different status of means after the performing arithmetic operations. So I hope it is clear, and suppose if you have any doubt, you can ask me now. Okay, we'll discuss. We can discuss once again. So arithmetic load, store operation, memory related. So there are two cases, and it is depend upon the 13th bit. If 13th bit is, if it is 0, if it is 0 means what happens? If it is 0 means the two registers and the destination register, all the three are registers. Suppose if it is a 13th bit is 1 here, 13th bit is 1, then one register and constant value, right? Yes, any doubt? Or shall I repeat once again? Shall I just give a summary? And here the main thing is that you have to remember all these tables. OP operation, OP code. 00 means set I and branch format. 01 means a call. 10 means arithmetic. 11 means memory format. But in set high and branch format, both are same. So once if both are same, means either it is set high or branch format. Then again there is a OP2 code. So OP2 code means if it is 100, it is a set high, and if it is 010, it is a branch related instructions, right? So in this way we have to difference. So this complete table for 8 marks you will get a question, 8 marks question. ARC instructions format. So in ARC, a RISC processor, there are two type of processors now. One is RISC and RISC. So this is a RISC, reduced instruction set, instruction set computer, a RISC type of processor. And here we will discuss about the format, okay, the format of these different instruction. So here only we are discussing the important the instruction formats. The first one is set high format, branch format. So to differentiate to identify the set high format or branch format, it is depend upon the 30 and 31st bit positions at the MSB side. If both are 00, it is a set high or branch format. So these two formats means it is identified by these two bits, and after that the OP2 code, it will differentiate again which is the branch instruction, which is the set high instruction. So for OP2, what is the value? 010 and 100. If it is 100, if this particular bit, if it is 100, then it is called as set high format. Set high format. And immediate 22 means here it loads the MSB most significant byte, 22 bits it stores here. 22 bit. There is reserved 00 to 21 up to 21, 22 bits. And this is the destination register, and just all the registers percentage are not to percentage are not to percentage R31, right? R31 total 32-bit register that we represent in a 5-bit. Like for example here percentage R5. So how we represent 0 0 1 0 1 means your computer will understand the binary format. Okay, it understands. So that's why the assembler, it will convert the instructions into this machine code form. Then similar to the branch instructions, it uses the 22-bit for the calculating the address, means where to jump. Then call instructions, then arithmetic instructions, arithmetic request, that is these 2 bits that will identify whether it is a arithmetic instruction or call instruction or it is a memory instruction. For arithmetic instruction it is 10, and for memory instruction it is 11. Okay, so I hope it is clear to all. Then arithmetic instruction, to add the 2 numbers, we have the source register 1, and we will get one more number in the source register 2, and after performing the addition we will get here destination register. And for OP3 operation, it will decides what is the operation. It is AND operation or add operation or operation. Okay, arithmetic. arithmetic and logical operations. And this particular bit will decide, the 13th bit will decide whether if both the content are from the registers RS1, RS2, or one is register and another is the constant value. Another is constant value. Okay. So similar to the memory instructions. So this question definitely you will get for your examination. What is the question? Write ARC instruction and PSR formats, program status, word status register. So this you have to write in a exam, this table. It is a 8 marks question for your examination. Then we will discuss data format, ARC data format. Okay, ARC data format. Okay, the same diagram there's enlarged here. Is it visible? Can you see? Yes, or shall I divide this picture into two parts? Yes, say anyone? Yes.
Sir, it's visible.
Okay. So signed. So this is the data format. Okay, signed integer. Integer byte. Byte means what? How many? 8 bits, right? 8 bit. So 0 to 7. Signed integer half word. Half word means 16 bit. Means 1 bit is reserved for the sign here. This particular bit is there, no? So that is reserved for the sign. Okay. Sign integer word 32 bit. Okay. So this is a data representation. Word means 32 bit. Then unsigned integer. Okay. The unsigned means by default it is a positive. Unsigned integers. Then floating point. Floating point. That you know, single precision floating point, double precision floating point, and there is one more quad floating point. So single precision means 32 bit, double means 64 bit. Okay. Yeah. Here it totally. Here 0 to 31 the fraction, and again 51 means total 0 to 52 bits are fraction, and then 1 bit for the sign, and 53 plus, that is 11 bit for the exponent. 11 bit for the exponent in double precision. Here 23 bits for the fraction here in single precision, right? 1 bit for the sign. 24 plus 8. Okay. So this is very important, huh? Single precision and the double precisions. Single precision floating point. Okay, in your gate also it is very important. Gate exam also. A single precision, sign bit 1 bit, exponent 8 bit, and 23 bit, that is fraction. Okay, 23 plus 8, 31, 31 plus 2. And for double precision, it's a 64. 64 means 53 one sign bit plus 11 plus 53. You have to remember this one. 1 plus 11, 11 plus 51, 12. 12 plus 52 means 64. That is a data format. Okay. Then one more important concept in pseudo operations in ARC processor. ARC pseudo operations. Okay, pseudo operations. Pseudo ops means pseudo operation. So what is pseudo operations? Pseudo operations are the instructions. These are the instructions to the assembler. They are not a part of the instruction set architecture. This is a part of the they are not part of the instruction. These are not instruction. These are the instructions to the assembler, but instruct the assembler to do an operation at the assembly time. Okay, these are the instructions to the assembler. Okay, for example, roll number 19. Row number 19?
Yes, sir.
Yes. So just I called roll number 19. Means I'm giving some instructions. Roll number 9. So there are around 65 students are there in the class, 70 students. So out of 70, who is responding now? Roll number 70, roll number 19, right? Means it is instruction to the assembler. Okay, these are the pseudo operations. Pseudo operation means these are the some of the code pseudo operations. Okay, pseudo operation to the assembler. Pseudo operation to the assembler while executing the program. The instructions are represented, like for example, add cc, percentage r1, percentage r2, percentage r3. What is this? This is the instruction. But these are the pseudo operations. Instructions to the assembler. Okay, and you are all of you are familiar with this, because when you write a program in a C program and all, you will write the hash include stdio.h, right? Yes or no? In Python only, I think you won't write any directly. You assign variable. You okay? But in C and all, you will write like start with the some like or in Java main function public static void main. Okay. So likewise in pseudo operation, these are the some operation dot equ. Okay. So dot equ means what is the usage here? X dot equ. X dot eq means the treat the symbol x as tag. Equivalent. Okay. So x is equivalent to 10 means we will assign the variable. No, for example, x equal to 10. In Python, we will directly write x is equal to 10 means the integer x will assign to the 10 will assign to the x, right? Similar to that, x dot equ, x dot equ 10. So what it indicates? X, the value means it is equivalent to 10. Then dot begin. Dot begin means start assembling process. Okay, dot begin. Dot begin means start the assembling. Dot end, stop the assembling process. Means begin and end. These are the start and start and end of the program. For example, I will show one here. This is the program. This program adds the two numbers. So this is a simple ARC assembly. Means it's ARC process, risk type of means how we can read the program here. Here we are not discussing in detail about the programs and all. We are just understanding the instructions and all. Okay, instructions and their operations and all. Here the begin. Begin means what? It starts the assembly process. Okay, like in C and all, you write hash include stdio.h. So it's similar to that. It will begin with dot begin. Then dot org 2048 means it will start with the address 2048. The location, address location that starts with the address location. It starts with 2048, right? Address location start with 2048. Then the program will start like load x. Okay, load the content of load x into the register R1. The memory location pointed by y to R2. Then perform the addition content of R1, content of R2, and store the result in R3, right? Then store that content of R3 to store R3 into the Z. Then jump to this particular location. Okay. So this is the result x, y, z means they're taking the values x value 15, y value 9, and z is 0 initially, and end of the program. So this is the how we write a program. Here, what are these pseudo operations? Pseudo operation is begin dot org end. So these are the pseudo operations. Okay, let us discuss. Okay, here this is the same diagram. Pseudo operation means it is instruction to the assembler. They are not a part of the instruction set architecture, right? So here dot eq that treat the symbol x equal to 10. Dot begin start the assembling, stop the assembling, change the location to the counter 2048, the address. This also we used in the program, right? So DWB reserve a block of 25 words. Reserve DWB means what it does? It reserves some space, block of 25 words. Then dot global y is used in another module, z is used in another module. Okay, some global variable declarations and all. Macro, so define the macro operations yum with formal parameters. End of the macro operation, some functions and all we'll write. Okay, macro function, micro function. Then it is started and end here. Then if conditions, dot if condition dot end if line 4. So these are the pseudo operations. So you may get questions, so 4 marks questions like define or list and describe the different pseudo operations, ARC pseudo operations. Pseudo operation means these are not instructions. These are the instruction to the assembler while executing the program. Okay. Then we'll discuss about synthetic instructions. ARC synthetic instructions. ARC synthetic instructions, right? So many assemblers will accept synthetic instructions that are converted into actual machine language instructions during the assembly. Okay, it accepts the synthetic instructions and that are converted into assembly language instructions. So very simple thing. What it does, synthetic means this is the synthetic instruction. This is the instruction. Okay. So this instruction is converted into a machine code form. Machine code form means this is the original instruction, synthetic instruction, and the instruction generated means what it does, it will convert into the machine language instruction. Okay, this is the original instruction, but what is the operation it does? XNOR RS1. What is suppose here? Just the first instruction. What is that? Not RS1 RD. Not means what? Not means it does the complement operation, right? Not means complement operation. So not this RS1 source. It take the data from the RS1 register and it does the complement and store it in the destination register. But actually what it does, it uses this operation XNOR RS1 with R0 or not. R0 means all are 0. Okay, and it stores in a destination register. So XOR operation means what? XOR means I think 0 0 0 1 1 0 1 1. XOR means both. This is 0, right? XOR means this is This is XNOR. So what it does, it takes the value from the RS1 and R0 means all are 0. It performs the logical XNOR by taking the content of RS1 or not and store the result in the particular destination register. Like for example, increment RD, increment INC RD is the one instruction, ARC instruction. But here actually what operation will do, happens here? Add RD to 1 means one constant will add to the destination register and it stores in a destination. I hope you understood this. Increment by 1, and here negative means it does the 2's complement. Decrement DEC RD means decrement operation, right? But what happens here? It uses the subtraction instruction, decrement by 1. So clear RD means clear means it is 0, right? So it uses C AND operation and RD R0. R0 means it is a register with 0. The value is 0 R0. So anything with 0 means 0 only, right? Here AND operation is there. AND operation is there. Okay, right? Anything with 0 means logical AND 0 only. Okay, so this is the synthetic instructions. So this is a synthetic instruction operation, right? Then so the same instruction means actually this is the original instruction, but during the assembly it is converted into this form, machine code form. Machine code form, and the operation is first complement. So this negative means is a 2 complement form. Increment means it will increment by 1. Here it uses the add operation, subtraction operation. Okay. Then this is the example that we discussed, right? So this is all about the third chapter. So this is not so up to this is for your as per the syllabus, and yeah, synthetic instruction just taken from the internet. Means this is for Spark processor, oracle.com or Spark processor. Okay, good morning to all. Today we'll discuss the cache memory and memory hierarchy concept. So that memory hierarchy and that cache memory concept that comes in your as per the syllabus, it comes in the third chapter only. So memory hierarchy and cache memory. Okay. So as you know, you people are already experienced with the cache memory. Means you people use cache memory sometimes in your personal devices. So can anyone tell what is cache memory? Have you heard the word cache memory? Yes. Ishita Jain, roll number 14. Roll number 14.
Yes, sir.
Do you know cache memory?
No, sir.
Do you have mobile phone?
Yes, sir.
Yes. So, like when you search for any any URL and all in your browser, so when
Yes.
you search, like suppose if you are repeatedly if you visit some particular page, okay, like for example WIT Solapur, that URL, and if you repeatedly if you visit that particular page, and so in your browser, suppose if you just type W, then automatically it will give some suggestion, right?
Yes, sir.
Means whatever the address that stores in a, means the frequently accessed data items, the frequently accessed that web page that stores in a cache memory. Okay, so cache memory means actually in your browser you can see sometimes you clear some your history and all. Okay, so the cache memory means it is a very small memory, and even I think in your mobile also you can see the cache memory. In your mobile also.
Yes, sir, I can see.
So cache memory means it is a fast memory. It is a fast memory compared to the main memory. What is main memory? Anyone? Can anyone say what is main memory? Yes, Prathamesh. Prathamesh, are you there? Vishwanath. Okay. RAM. Random access memory. So that is a main memory. Then yeah, secondary memory. Secondary memory. Omkar. Nitish. Secondary memory, read-only memory. Okay. So, like suppose now, so you people told about a different type of memories, like cache memory, primary memory, and secondary memory, right? So, as we just now we discussed, cache memory means it's a very small memory. Cache memory is a very small memory. Primary memory, the size of the memory is large, and secondary memory, okay, so this is a cache memory, and this is main memory, and this one secondary memory. Your hard disk and all, or pen drive, it stores the large amount of secondary memory, right? So here the user what he does, he access the data, he search the data. So when the user searches the data, first it searches in the cache memory. Okay, it searches in the cache memory. Okay, so it is this cache, main, and these are all types of memories. So when the user it searches the data, first it initially searches in the cache memory. So if the data is not present, if the data is not present in the cache memory, what it does, it will go to the main memory. Okay, and again if the data is present in the main memory, then the the user will get through cache. It will store in a cache and user will get the data. Even if suppose if the in main memory it is not present, then it will go to the secondary memory. From secondary memory to primary memory, and primary to cache, and user will get the data. User will get the data. So in real time, if we consider in the real time, suppose like you consider library. Okay, there is a one library, and the Prathamesh. He is the Prathamesh. He is accessing. He is issuing a book from the library. He is issuing a books from the library. Am I audible? Yes. Am I audible? Say anyone else? Okay. So just general example. Here, just a general example. Here, the Prathamesh is issuing a book from the library, and the librarian, what it does, like for example, now you are in the third year. Third year, which semester? Third year, first semester, right? So he will keep all the books that are related to the third year first semester, like COA book, SS subject book, operating system, okay, Python. So all these books that are using in this particular semester, he will keep near to his rack. Okay. So the library means, you know, it is a like it is a the different type of racks where the different type of books are placed. Okay, this is different racks. Okay, this is it contains the racks together books. Okay, different. So the librarian, what he does, he will keep the data or the books that are frequently accessed in this particular semester. Okay. So for example, for first semester, these are the books: COA, SS, operating system, Python. All these books he will keep near in his rack. Okay. So whenever the particular person, like for example, the Prathamesh, if suppose Prathamesh is issuing the books, then what happens? The librarian, he won't go inside these racks. Okay, he won't go inside the racks. Okay, these are the different racks. So he won't go inside the racks to search for the books. He will just take the books from the rack near to him, and he will issue those books to the Prathamesh, right? So next, one more person will come, like Madhuri will come. So again, so Madhuri will also issue some books, like for example, software, system software. So again, the librarian, what he does, he will issue the books that is, because it is available in the these near to the librarian, near these racks. Okay, he won't go inside these librarian, inside the library to search or to find the books, because the librarian, what he has done, he kept the frequently accessed books, because in this particular semester, because he know what are the books is required, okay. So based upon that, the frequently accessed books he will place in the near to his rack. So the issuing the book here, the main advantage is that the issuing time is very fast. Okay, he's not going inside these library and searching for particular books. Okay, he's not going. So suppose in the suppose in the second semester you have a software engineering subject. Okay, you have a software engineering subject. Suppose Abhishek will come now. Now Abhishek, he's interested to, like, in first semester only. In the first semester only, he wanted to go for some software engineering concepts. So now the Abhishek will come. Abhishek will come and he will issue for software engineering book, because the software engineering, it is not available in the cache memory. So librarian, what he does, he will go to these racks. Okay, then he will find the software engineering book. He will, in this means here, even like he will cross all these paths. He will check in the cache memory. Cache memory is not available. Then he will check in the main memory. Software engineering, it is not available. Okay, software engineering is not available in cache memory, and because this is not a frequently accessed item, right? Then he will go to the secondary memory. Yes, it is available. Then he will place in the main memory and in the cache memory, and he will deliver the books to the Abhishek. So I hope you understood this concept, because the main advantage of the cache memory is that the response time is faster. The response time is faster, but the size of the memory is very small. The size of the memory is very small for the cache, and this is called as a hierarchy. Hierarchy means, like, this is the small memory. Okay, this is the cache memory. Then after this, the main memory will come. Okay, so this diagram only horizontal is there, no? You just imagine in a vertical. Okay, the hierarchy of the memory means this is a very small memory, and it is in terms of KB, or in MB also, 1 MB or like. Okay, and the main memory is around like 256 MB, and here it is in terms of GB. It is in terms of GB. GB means it's a large memory, so it takes time to find the particular item, right? So I'll directly come to this memory hierarchy concept. So memory hierarchy means here we use some terminology to store the data, like registers in CPU, and internal or main memory. Okay, main memory that may include the one or more levels of the cache. So that is RAM, and external memory means like the hard disk and all we can consider. So I hope this is visible, this diagram. Is it visible? Say anyone else?
Yes, sir.
Okay. So here this is the hierarchy of the memory. Okay. This is the hierarchy. So what is the first step here? The registers. Registers, very small registers that store the data. Okay. Then after that, the memory will come, that is cache memory. Okay. So first will come the registers. Registers are very small memory. Then comes the cache memory. Then main memory. Okay. Then secondary memory. Then offline storage, external hard disk and all you can consider. External hard disk, offline storage. So here the registers, the register, the time, access times, you can consider it 1 nanosecond. Means it's a very small memory. Okay, very small memory. So the response time, the access time is very fast. And next comes the cache memory. The access time is 5 to 20 nanosecond. Okay, 5 to 20 nanosecond. And the main memory again, because here the size is increasing. Here you can see in the triangle shape. Triangle shape means what? The register, the size is very small. Okay, and here the storage means hard disk and all. You have the 500 GB hard disk, 320 GB hard disk and all. Okay, so it is in terms of KB, 1 KB data. Okay, the register that stored the data of 1 KB, and here it is in terms of like suppose a 240 GB hard disk. So that's why it is in a triangle shape. It is in terms of triangle shape. Okay, cache memory, main memory, and all like. So registers, the time access time is very fast. Then cache memory again. So the time speed little bit it reduces because the cache memory takes more time, 5 to 20 nanoseconds. Then main memory that takes around 60 to 80 nanosecond. Suppose for this is the case, like the what is the size of the memory? 64 MB. Here the register, what we consider, registers 1 KB size, cache memory 1 megabyte, main memory 64 megabyte, and the disk memory we considered as 4 GB. And here the first thing is that the fast. Okay, these the access is fast in the register. The access time is fast in the register, and in the disk memory it is slow because the memory size is very large. Okay, then it is faster. Register cache memories are all faster. Disk memory is slow, but it is faster, but it is costly, expensive. Okay, if it is fast, if you want fast memory means you have to pay more, and it is slower means it is inexpensive or okay, inexpensive. Okay, so normally like when you purchase a mobile phone, so if you go for like higher the memory like 8 GB RAM, 6 GB RAM. Okay, so the cost of the memory is, the cost of the mobile is more, around 20,000, 25,000 and all. Okay, and suppose if you purchase some like 2 GB RAM, 3 GB RAM, then the cost is less. Cost is less. Means if you want the faster, if you want the like to play the game and all, so you prefer some high speed memory, right? High speed memory. So if you want fast, then you have to pay more. The expensive, and slow means inexpensive. Slow means the hard disk and all. Okay, so that you can like even we can like say general examples like suppose in your IT department, IT department third year. Okay, like in your class we can find the like Abhishek is the only one person. You can immediately find out of 70 students, one student we can find very easily. Okay, suppose in Okay, so this is a class, and this is a WIT. This is TY class, and this is WIT. So if I want to find the Abhishek, okay, so in this particular, because only 70 students are there, so I can find very easily the, okay, the response time is very fast in this particular class. But if we don't know, means in which class he is, in WIT or like IIT department, CSC department, ENTC, electronics, mech, civil, so you will get 10 to 15 Abhisheks. And to confirm which Abhishek you want, okay, it takes more time. So this is a cache memory. This is a secondary memory. This is a secondary memory. You will take more time. You will take more time to find the data. So I hope you are understood. So the memory hierarchy means this is the hierarchy in the triangle shape. The registers, cache memory, main memory, secondary storage, and offline storage. And now you can include one more thing. What is that? So in the cloud storage also you can add, but for that cloud storage, here also you can store the huge amount of data, but it will be expensive. Here means here we are not mentioned that online storage. Online storage means that you can store the data, but you have to pay the money. You have to pay the charges amount to get some storage space. Okay. So in our college Moodle server, I think it is in terabyte, the Moodle server, the memory size. Whatever you do some assignment submission, your LCM activity and all that you access from the Moodle. So the size of that, the memory size of that server is, it is in terms of the terabyte. So that's why still you people are not facing any problem for accessing the data and all. Even you people are submitted your answer sheets, right? In terms of MB, it is in terms of MB size. So this is about the memory hierarchy. So you will get a question in the exam. With a neat diagram, explain the memory hierarchy. So what is the first level of memory? The first level, that is the registers. Okay. Then cache memory, then main memory, then secondary memory, then offline storage. Okay. And and if you suppose if you want some the high speed memory, then you have to pay more. Means you have to pay the more amount of money to get the faster access. This cache memory and all, the cost will be more. But response time is very fast, right? The response time is very fast. The registers, cache memory. So register cache memory has, you can see the size triangle shape. So at the bottom, the size is large, but it is slow and inexpensive, less costly. Slow and inexpensive. But registers are, it is a fast memory and expensive. I hope this concept is understood by you all. Okay, so this is one type of diagram. Here in this way also you can write the triangle shape. Registers, cache memory, main memory, okay, very small memory. Then that comes the storage like magnet CD-ROM, DVD-ROM and all. Then the offline storage. But in the exam, you go for this diagram. Register, cache, main memory, secondary disk, offline storage. Okay. Register is a fast memory. Register is because memory is very small. It is a fast and inexpensive. But here, the storage, the hard disk and all, it is slow, but it is a inexpensive, slow. But in what we expect, the memory, it should be faster and it should be less, right? What our goal? Our goal is that we want the faster access of the data, and also it should be inexpensive. It should be inexpensive. Yes or no? But here, for this, we need to use some memory techniques. We need to use some memory techniques to get the data faster, and also it should be less costly. Faster access means the response time. Okay, the response time, how you get the data. But in case here, the fast memory is a costly. These are all okay. Even in the RAM only, suppose if you buy a smartphone of 8 GB RAM, so you have to pay more money, right? Around 25,000 rupees. 25,000 rupees you have to pay for 8 GB RAM mobile phone. And that to suppose if it is 2 GB, 10,000 rupees, 10 or 8,000 rupees you can pay. Means 8 GB means it's a faster memory. If you want faster, you have to pay more. You have to pay more, right? But there are some techniques are there so that you can achieve the faster access from the secondary storage. Some memory mapping techniques are there. Okay. So that the pipelining techniques and all means we have to design the memory design. We have to organize the memory such a way that we can get the data faster, right? Then here we consider some of the parameters like access time of the data access time. What is access time means what? The time between presenting the address and getting the valid data. Means here this is suppose a memory, and here the user means he is requesting data in a computer. He is accessing the data. So user accessing the data means with some address. Okay. So the accessing means the time between presenting the address and getting the valid data, getting a valid data from the CPU. So that is called as access time. Then memory cycle time means the time may be required for the memory to recover before the next access. Okay. So whatever the presenting the address and getting the valid data. Okay. Then after that again you will go for the finding the data from another address. So the time may be required for the memory to recover before the next access. So that is memory cycle time. So cycle time is access plus recovery. Recovery means before starting the next data access. Okay. So that is called as memory cycle time. The transfer rate, the rate at which data can be moved, that is transfer rate. And see, these are some of the memory types. Semiconductor, that is RAM. RAM means it is a semiconductor memory. Magnetic disk, the secondary hard disk and all, it's a magnetic device. CD, DVD, it's optical. Okay, and you won't use, I think, bubble hologram and all. I think you people are familiar with these: RAM, hard disk, CD, DVD. Then physical characteristics: decay, volatility, erasable, power consumption, volatility, memory, erasable, and all. Okay. So here the main thing is, okay, so this is the hierarchy of the same, they are written in detail. Okay, the hierarchy of the memory, right? So here the register will come. Then here they are divided the cache memory into two types: L1 cache memory and L2 cache memory. So even in your computer also you can check, there are two type of cache memory: level 1, level 2 cache. Means what happens when the user requests the data, first it will check in the L1 cache. If suppose if it is means it is very nearer to the user, if it is data is not present in the this level 1 cache, then it will go to the level 2 cache. Okay, so a register, then this is a cache memory, then it is a main memory, then yeah, disk cache and all that comes in the here disk, hard disk, secondary storage, hard disk, optical and all. Yeah, here actually optical will come, optical, and here hard disk will come, secondary storage, hard disk and offline storage. So it is with respect to the size. Here the size of is very small, the size of the memory is very small, and here it is large. The size of the memory is very large. Okay. So this is the hierarchy. So you want fast. It is possible to build a computer which uses only the static RAM. So this would be very fast, but this would be no cache, and but means if you want only that particular the system with the RAM or cache memory, the cost is very large. As I already told, if you want the fast like 8 GB RAM, it cost will be more, 25,000, and for like 3 GB RAM or you will get like 10K. Okay. If you want faster memory, the cost will be more. Right. Then locality of reference. Locality of reference means this is the locality of reference. We call it as locality of reference in cache memory. So here the CPU, that is user accessing the data. So first he will find in the cache memory, and if it is not available, then it will go to the secondary memory, and from the secondary memory again it will store in the cache, and it is delivered to the CPU. So this is the cache memory definition. So in the exam you read this diagram for cache memory. It is a small amount of fast memory. The cache memory, it sits between the main memory and CPU. This is the main memory, and this is the CPU. Okay, like in the library, if you consider library, in the library what happens? This is the large number of racks, main memory, large number of racks, and it is a very small rack near to the librarian, small racks near to the library, and here the user will come and he will access the data. So librarian, he will initially check in the small racks. If the data is present, then he will transfer. So very less time. If the data is not present in this small rack, the librarian will go to the large number of racks. Okay. Then he will search in this particular the different racks, and he will keep the similar type of data in the means if it suppose if it is frequently accessed, if more people are requesting the same type of textbook, then he will keep in the his cache memory and he will deliver. Okay, so that library means it is general example. The library concept is there, no? That is a general example to understand how the cache memory works. Okay, so cache memory, it what it does, it stores the frequently accessed data items. So whatever we do, like for example, if you are checking the COVID-19 the status, okay, you are daily if you are checking the COVID-19 status means in your Chrome browser also, it will create a bookmarks, no? It will create a bookmarks. So in the next time you no need to type, just if you click on that particular URL, you will directly access. Okay, so means whatever the suppose if you visit the YouTube's regularly, YouTube or any other websites and all, then it will it will store in a bookmarks, and whenever you go, just click. Means the response time is very fast. Okay, so this concept is very important, the cache memory and memory hierarchy.
So memory hierarchy. So in memory hierarchy, what type of like the memories are involved? The registers, cache memory, main memory, disk cache, disk memory, optical, and tape. Okay, so in the memory hierarchy. Okay, so this is the memory hierarchy diagram where the registers, very small size memory, registers, cache memory, main memory, secondary memory, offline storage. Okay, so this concept we have discussed, and here the registers, the memory size is very small, so the response is fast. The response is fast, but it is costlier. It is costly. What is the registers and all? The registers, cache memory, these are all, the memory is very fast, but it is costly if you compare with the secondary. The here it is a slow, but it is a inexpensive. Okay, so these are the contents we discussed in the last class. Okay, registers, cache memory, main memory, it is based upon the size. It is a triangle shape. Okay, it is based upon their size. Based upon the size, where it is written a triangle shape. That is memory hierarchy concept. Memory hierarchy. Okay, so these are the concepts we discussed, and the cache memory, we discussed about the cache memory also. So cache means a small amount of the fast memory. It sits between the CPU, central processing unit, CPU, and main memory. So this is called as cache memory. Cache memory, it sits between the main memory and the CPU, and it may be located on the CPU chip or the module. So there is a data transfer between whenever the CPU requests the data, first it will search in the cache memory. Suppose if in the cache memory, if it is present, then it will give response to the CPU. If it is not present, then it will go to the main memory, and then it fetch the data. Okay, so that is the cache memory operation. So this is the structure of the cache memory and main memory. So here you can see like in this cache memory, the structure is, it contains the tag field and the block, the memory tag field and block. Okay, and in the main memory also, there is a memory address. There is a memory address and the block of the, like, different memory address, like these are the memory addresses. Okay, up to 2 raised to n minus 1. Each memory address, it stores some data. It stores some data, right? Some hexadecimal data, right? So here the cache memory means the tag field and block. Okay, the structure of the cache memory. Cache memory means it's a very small memory. Main memory, the size will be large compared to the cache memory. Okay, suppose in general, if you compare in the general, like suppose here, suppose this is one particular area. Okay, like suppose it is some apartment. You consider the some apartment or college. Okay, college, it is one college. College contains some departments. Okay, there's so many departments. So here it is a main memory. College means main memory. Main memory. Okay, main memory means here all the departments will come, office will come. Okay, it is office. Okay, so it is a college, a complete college. And suppose if the one person, if it is requesting the data like IT student, second year, roll number 19. This is the data we had to fetch the data, IT department, second year, roll number 19. So if we search in the college means everything will come, department, office and all. IT second year 19. If we search in the college, it will take more time. Okay, means so if we find this particular this person 19 roll number, suppose if we have these taglines, we call it as a tag, just fields, IT department. So instead of going to different departments, what we do, we go to the IT department. So it saves our time. Okay, it saves our time, right? It saves our time. So IT department, and after that, IT department also for first year, second year, third year, final year. Suppose if we have the second field, SY, then directly we can go to the second year. Okay, directly we can go to the second year. Department, class, right? Department, class, then we can easily fetch this data out of 60. Okay, we can fetch the data. So cache memory means it is like a very small memory and will identify with the tag. For example, here we require some data like IT department, IT second year. This is address, second year, roll number 19. So this main memory contains, like suppose this is mechanical department, this is CSE department, this is IT department. Okay, So if I search, I want to, what is the CPU? CPU is requesting some data. What is that? CPU is requesting the data this particular address. Okay. So if this tag field, if this value, if it is matching here, okay. If this particular, like this is the user requesting data, IT second, I'm just taking general example. Huh? This is my address. I have to fetch this data. CPU is requesting their data here, this 19. So first it searches in this cache memory. If the data is not available in the cache memory, then it will go to the main memory. Suppose just consider that this data is not available. Cache memory mein nahi hai. If it is not available in the cache memory, then what it does, it will search in the main memory. Search means it will start from here. So it takes more time. Suppose if we have this tag field, then directly it will come to this particular block, and in IT department again SY, TY, B. So we have that inner data also SY. And again as SY again 60 members. So we can find easily this data. This first it will search in the cache memory. If the data is not available in the cache memory, then it will come to the main memory. Okay. So that's why these fields are very important, the tag field and all. Okay, so I hope you understood some concept. So that's why here is a black block of words. You can see there's a block of words. So this is like block of words. So here actually in what happens in this cache memory, yeah, here this is the some like mapping. So before that is better we will discuss some concepts. Okay. So the CPU it is if the CPU accessing data, first it search in the cache memory. If the data is available, then it is delivered to the CPU. If it is not available, it will fetch from the main memory, right? So this is the structure. Okay. So operation क्या है? The CPU requests the contents of memory location. Check the cache memory for this data. First, it will check the cache memory because the cache memory it is near to the CPU. Cache memory is near to the CPU. So first, it immediately checks the cache memory. If the present, get the data from the cache. So that is a faster response. If it is present, the response will be faster, right? If not present, read the required block from the main memory to cache. If it is not present, where to go? If the data is not present in the cache memory, then it will go to the main memory. Main memory. It will go to the main memory. So this is about the cache memory and main memory. If the data is not present, read the required block from the main memory to cache. Then deliver from the cache to CPU. Deliver from the cache memory to CPU. So cache includes the tags to identify which block of main memory is in the cache slot. It uses the tag field to identify, for example, this particular field, it may be available in this particular block. So here there are so many blocks, like this particular, it will be available in this block, this particular line. Okay. So cache includes the tags to identify which block of main memory is in the cache slot. is in the cache slot. Okay, so this is the flowchart of how the cache memory read operation takes place. So it receives the address from the CPU, then is the block that containing that address in the cache, means it will check whether like the CPU it will check to cache memory, then cache to main memory. So the CPU, that address, it will first check in the where, in the cache memory. It will check, yes, if it is present, yes, then read the word and deliver to the CPU. If the data is present, then it will deliver to the CPU, right? If no, access the main memory block from the block containing the receiver address. Here it will go to the main memory, then allocate the what is the fetch data in the cache memory, and then cache memory to CPU. Very simple. So whatever the concepts we discuss now here, the same it is represented in a flowchart. So for this design for designing this cache memory, because the cache memory is costlier, it is a very small memory. Okay, it is a costly. Okay, so what we do, we use some techniques, mapping techniques. We call it as mapping techniques to improve the speed. Okay, so for that there are some like algorithms, are the replacement algorithms and all. Okay, so here the size does matter for cost, because cache is more expensive and it is faster. Okay, yeah, the cache memory organization, processor, cache memory, and here the main memory. The same that flowchart, it is represented in this format. This is very old data, that is up to 2004, means the different processors are having the cache memory L1, L2, L3 cache. In the cache memory also, it is the levels are there. Like for example, if it is a CPU, then near to the CPU there is a L1 cache. Then L2 is too far, it is far from the L1. Then L3 cache. Okay, and then main memory. In this way, main memory. Are you getting the main memory concept? Okay. If just cache memory means it is like one cache, but in the cache memory that is levels, level 1, level 2, level 3. Level 1 means it is very near to the CPU. If the data is not present in level 1, go to level 2, level 2, level 3. Here the some of the processors, the old processors are having the only L1 cache up to Intel 80486. You know, 486, 386, 286 processors. It is having only one memory, that is L1 cache. And other processors are having the L1 and L2 also memory, 8 KB and 256 KB. This is 8 KB and the second is 256 KB. So similar to that, nowadays the modern, even your mobile devices, computers are having the different type of, like a different type of cache memories. Okay,